Okay, so it might not feel like it, but what we've actually done now is we've built a whole new system of arithmetic. So we're all used to the arithmetic we know and love with ordinary numbers, and there's certain rules we use when we're working with ordinary arithmetic. We've now developed a system of matrix arithmetic, and it's important that we enumerate the rules we're allowed to use. So the first rule I want to list here for matrix arithmetic is the additive associativity rule. All this says is that if you add three matrices together, it doesn't matter how you group the parentheses, you'll always get the same result. And this is exactly how the addition of ordinary scalars works. So we shouldn't be surprised that we have this particular rule. The next rule is multiplicative associativity. What this says is that if we multiply three matrices together, and we're allowed to do it, it doesn't matter how we group the parentheses. So we can, if we're multiplying A times B times C, multiplying A times B first and then multiplying by C is the same thing as multiplying B and C together first and then multiplying on the left by A here. So we can always group parentheses however we like, which again, it might not seem novel because that's how scalar multiplication works, but it's important to make note of. There's additive commutativity. This is just a fancy way of saying that when we add two matrices together, it doesn't matter which order we do it in. We also have distribution laws. So let's say that we decide to add two matrices, B and C, together, and then we wish to multiply by matrix A on the left. The left distributive law says that's totally fine, and in fact, that's the same thing as first multiplying A on the times B, and then multiplying A times C, and then adding the results up. So we can distribute matrix multiplication from the left. We also have a right distributive law. So if we want to add A and B together and then multiply on the right by C, that's the same thing as multiplying A times C and then B times C and adding the two results together. So not only can we distribute from the left, we can also distribute from the right. And there's also the transposition rule. So this might be the first real interesting rule. The transposition rule says if we want to multiply A times B together and then transpose, that's cool. And that happens to be the same thing as individually transposing the matrices, but not multiplying them in the same order, multiplying them in the reverse order. So AB transpose is the same thing as B transpose times A transpose. So this is the first encounter we have with an operation that does this. So remember, when we first learned about transposition, one of the very first properties we covered was its involutive property. This is the property that said if you transpose twice, you end up just with the original thing. So transposing twice never does anything. What we're encountering now is this order reversing property. If you want to transpose the product, that's the same thing as the product of the transposes in the reverse order. So if you want to be fancy about it, what you could say is that transposition is an order reversing involution. So those are some properties that hold for matrix multiplication. There's something like glaringly missing here. Note that we have this rule for additive commutativity, which says it doesn't matter what order you add things in. And one thing that we're all accustomed to when we work with ordinary numbers is multiplicative commutativity, meaning it doesn't matter which order you multiply two numbers in, you always get the same result. Well, the world of matrix arithmetic is much more complicated. So here's an example to illustrate why. Here's an example of a 2x2 matrix A and a 2x2 matrix B, and I went through the trouble of doing the matrix multiplication for these two matrices. And this produces the zero matrix. So right off the bat, that's actually kind of interesting. If we have two numbers and we multiply them together and get zero, one thing you can conclude from that is that one of the original numbers had to be zero. Evidently, that's not true in the world of matrices. Here we have two matrices that are not the zero matrix. We've multiplied them together and we've produced the zero matrix. So that's interesting. Maybe even more interesting, or at least as interesting, if we take those same matrices, A and B, and just swap the order that we multiply them in, that's still fine here because everything is a 2 by 2 matrix. So we know we'll produce a 2 by 2 matrix, but not the same 2 by 2 matrix. A times B produced the 0 matrix, but B times A does not produce the 0 matrix. In this case, it produces this other 2 by 2. Depending on how you view it, this is either extremely interesting and cool or kind of disturbing. When we're working with matrices, we can no longer rely on some of the intuition we developed from ordinary arithmetic. We cannot rely on A times B equaling B times A anymore because matrix multiplication is not generally commutative. So this is a huge warning. Matrix multiplication is generally non-commutative, and what this means is that we cannot rely on A times B equaling B times A. In general, A times B will not be equal to B times A. And that's all fair and good, but remember, this has consequences. If you assume that the order doesn't matter when you multiply two things together, you might end up making some oversimplifications on problems. So for example, here we have an equation where we're multiplying A times B times A times B times A times B times A. Well, if these were just numbers, if these were ordinary numbers, you might look at this and say, well, that's kind of a mess. I really have 1, 2, 3, 4 copies of A here, and 1, 2, 3 copies of B. So that should just be the same thing as A to the 4th power times B to the 3rd power. But the only reason you would be allowed to do that in the world of ordinary numbers is that it doesn't matter what order you multiply numbers in, you always get the same result. Since matrices do not commute, meaning that you cannot rely on A times B equaling B times A, we cannot simplify this expression on the left and obtain the expression on the right. So it might very well be that A times B times A times B times A times B times A is not equal to A to the 4th times B cubed. So we have to be extra careful when we're simplifying expressions of matrix products, because we might accidentally fall back on the intuition we developed from the world of ordinary arithmetic and oversimplify an expression. And again, this is one thing that makes matrix arithmetic more difficult than scalar arithmetic, but it also makes the world of matrices a little bit more interesting and fun to play with than the world of ordinary arithmetic. Another property that I want to state right now is called the Gramian of a matrix. So by definition, the Gramian of a matrix is the matrix, which sometimes maybe we'll just call G. This is the matrix given by multiplying the transpose of the matrix, the original matrix A, by the matrix itself. So the Gramian of A is just A transposed multiplied by A. The idea is that you're always allowed to do this, and what we'll find throughout the course is that this matrix ends up playing a shockingly important role in a lot of different theories. So here we have an example of a Gramian calculation. Let's say that the matrix A that we're starting with is this 2 by 3 matrix, where the columns are 4, -6, 2, -1, -2, -2. Well, so the matrix here is 2 by 3. When we transpose, we get a 3 by 2. And what happens when we multiply a 3 by 2 with a 2 by 3? We produce a 3 by 3 matrix. And one thing I want to point out here for this just tiny example we're doing, here I went through and I did all the arithmetic to figure out all of the entries in the product. Here we end up with a square matrix, so we have a 3 by 3 matrix. And if we stare at the diagonal for a second, we might not see anything particularly interesting about the diagonal. Maybe we do, maybe we don't. But something else might, there's something else that we might notice, and that is there's symmetry across the diagonal here. We have a 14 in the 1, 2 position that pairs with a 14 in the 2, 1 position. We have a 4 in the 1, 3 position that pairs with a 4 in the 3, 1 position. And we have a pair of -2s that occur in the 2, 3 position and the 3, 2 position. What do we call matrices that have this property? These are called symmetric matrices. So it turns out that if we want to transpose the Gramian, well, the way this would work mechanically is we would take A transpose times A and then transpose. And remember the order reversing property of transposition. when we multiply two matrices together and then transpose, that's the same thing as individually transposing, except we have to reverse the order. So here, we're reversing the order of A and A transpose in the parentheses here, and then tacking on a transpose. So now we get A transposed multiplied by A double transpose. But remember, transposition is also an involution, which means that the double transpose is equal to itself. So now we're looking at just A transpose times A, which is the Gramian. This is the one-line proof, which only needs two equal signs, that the example we're looking at here is not rare. This always works. So the first interesting thing we can say about the Gramian of any matrix is that the Gramian of any n by n matrix is always an n by n symmetric matrix. So if the matrix we're working with has 10 columns, its Gramian will be a 10 by 10 matrix, and that 10 by 10 matrix will have to be symmetric. So this is the first sort of introduction to this idea. I want to introduce this idea early because we're going to encounter it a lot, and I want us to just be familiar with this language in this property of symmetry right now, so we can be more comfortable with it down the line. Now, I want us to take an even closer look at the Gramian. So if we're taking A transpose and we're multiplying by A, if we think about what that entails from the row perspective of matrix multiplication, what we're really doing is we're taking every column of A and then taking an inner product of every column of A. So like the 1-1 entry of the Gramian is really just the inner product of the first column of A with itself. And if you remember about inner products, when you take an inner product of a vector with itself, that's really the length of that vector squared. In the 1-2 position, we're looking at the inner product of the first column of A with the second column of A. If we're looking at like the 1n position, we're looking at the inner product of the first column with the last column, and then so on and so forth. You can build every entry of the Gramian by taking inner products of the columns of A with themselves. So that can be summarized with the statement that the ij entry of the Gramian, A transpose times A, is really just the inner product of the ith column of A with the jth column of A. Okay, so that's Gramians. Another thing that will turn out to be useful is to view inner products themselves as matrix multiplication. So remember, from our perspective, when we're working with vectors, we're working with column vectors, which are really the same thing mathematically as n by 1 matrices. So here we're confronted with two vectors with n coordinates, v and w. And again, even though we're writing these as rows, we're using this transpose notation. So if we wanted to, we can view these as n by 1 matrices. And what I want to show you now is, well, what happens if we take v transposed and multiply by w? So v is an n by 1 matrix, which means when we transpose, we get a 1 by n matrix. And w itself is an n by 1 matrix. Well, are we allowed to take a 1 by n and then multiply by an n by 1? Absolutely, yes. What is the result? The result should be a 1 by 1. And how do we get that 1 by 1? Well, we just take an inner product of the two vectors. So that is to say that taking a vector transposed and then multiplying by another vector is the exact same thing as taking the inner product of those two vectors. This will turn out to be a useful idea. So the major takeaway here is that inner products can be written as matrix multiplication. The inner product of v with w is, from the matrix multiplication point of view, the same thing as v transposed multiplied by w. And again, what we're doing here is we're viewing the vectors themselves as n by 1 matrices. Now, this may seem silly, but it has consequences. In particular, remember one of the properties we mentioned when we introduced inner products was the so-called adjunction formula. And what that formula said was that if we're ever using an inner product and there's a matrix inside, we can move the matrix from one side to the other, but when we do that, we have to transpose the matrix. And when we introduced that I just stated it as a fact and moved on. But what we can do now with this perspective of matrix multiplication is actually prove the theorem. So I want to walk you through this proof line by line. So what we're trying to do here is we're trying to start with the inner product, A times V, with the vector W. Well, according to the matrix multiplication formula for inner products, this is the same thing as the vector on the left transposed. So that's A times V quantity transpose multiplied by the vector W. And remember, transposition is order reversing. So I can distribute the transpose here, but when I do so, I have to reverse the order. We also have the associative rule, which says I'm grouping my parentheses in such a way that I'm multiplying V transpose times A transpose first here, but that's the same thing as multiplying A transpose times W on the right here, and then multiplying by V transpose on the left. But now this is the same thing as V transpose multiplied by this other vector, and according to the matrix multiplication formula for inner products, this is the same thing as the inner product of the vector on the left here, V, with the vector A transpose times W. And that concludes the proof. This tells us why A times V inner product with W is the same thing as V inner product with A transpose times W. The formula for inner products can be viewed from a matrix multiplication perspective, where we transpose the first vector and then multiply by the second vector as matrices. And one consequence of that formula is that we can more easily manipulate symbols as matrices.